Right, that's what I'm waiting for. Okay, having spoken last week about how the CAPM model was developed and how it was really based on a distortion of the vision of behaviour that von Neumann and Morgenstern developed back in the theory of games, and why when you look at it properly, it's quite irrational to do what you're told is rational in conventional finance, which is maximise expected returns. What I'm going to go through this week is show how the data ended up finally, even though it was used initially to say you could actually justify the CAPM despite its absurd assumptions, finally the data destroyed it. And the ironic thing is most academics are still not willing to admit that it's been destroyed, but it's quite clear that it has been. So the CAPM assumes an efficient market. And by the word efficient, of course, this is one of the distortions of economic theory, the extent to which it will use a word that's in common usage and has a nice sense to it, like, for example, perfect or efficient, and then use it for a totally distorted purpose inside its own literature. So the word efficient to most people implies things done very quickly with a minimum of waste. Okay? In neoclassical economics, efficient means able to predict the future accurately. Bit of a difference. But if the market theory was right, and it was therefore efficient in general, all you see is a trend with the trend of the market to rise over time, with share prices bouncing around it, subject to some unpredictable shocks. And the shocks themselves, you can predict it. Even if you're saying you predict the future, you can predict the statistical average of the future. Now, therefore, you can't say what random shocks are going to come in as well. You've got a model of the economy rather than a model of sunspots or meteor showers or God knows what else that can disturb the system. So there'll be changes due to shocks outside the economy, but they should be within a fairly normal distribution range. And one thing which I don't know how much you've had this drilled into you, but if you say things following a random distribution, which is Gaussian, or the standard distribution that ultimately conforms to a Gaussian or converges with enough samples, events which are plus or minus 5 standard deviations away from the mean are so rare that you can forget about them completely. If you ignore events that are plus or minus 5 standard deviations away from the mean, you ignore nothing of importance. Okay? They are so rare, events outside that range, that you completely ignore their existence and still very accurately characterize whatever system you're describing. Now, the reality is that the markets have much larger shocks than that. So they're not efficient in the way that economists mean, even though they might be efficient in the way we think about the word, or normal language does, which is, does do things rapidly, fast assimilation of data, that sort of thing. And one of the key pieces of data which you're told to ignore in CAPM could be what other traders do and believe, because in CAPM, of course, you're told that everybody has exactly the same expectations about the future, and they're all completely accurate. In which case, why would you bother talking to anybody else? Because they say, I'm going to do what you're doing. So CAPM basically says ignore the behaviour of other traders. Maybe those are the behaviour of the other traders are the most important thing going. So CAPM became the efficient market hypothesis. And part of what it was seen as its strength when you talk with academic economists, they'd say, well, why is it so hard to make profits in the stock market? And CAPM explains that by saying there's no advantage, there's no misinformation to exploit, because the market includes all the accurate information, and there's no mispricing therefore to exploit, therefore you can't make a profit. Now, there's an alternative view which is very, very different, giving an answer to the same question, and that is the markets can be chaotic. There's so much volatility, so much unpredictability in the system itself, which is not random. It's such a complex system that you can't predict it. Even though there is information there, if you did know the system, you could actually exploit it. Most of the time, information is too complicated to be possible to exploit. So there can be two very different explanations for the same overall phenomenon. So which one is it, chaos or efficiency? Well, if you have very, very strong feedbacks between people's behaviour, or one thing leads to another and comes back and pushes the thing that caused the first change, what they call a positive feedback loop, they can't possibly be efficient, because an essential part about the idea of efficiency is the system is close to equilibrium or in equilibrium. Therefore, there's very little disequilibrium to exploit. Now, you can have a system which has got these strong feedbacks and is miles from equilibrium, but still very difficult to exploit because of the distance that are away from equilibrium and how fast they change as a result of that. So you can get unpredictability from being a long way from equilibrium as well, and therefore difficult to make a profit, just as it can get difficult to make a profit because it's very close to equilibrium. The big difference is if it's a long way from equilibrium, then the forces that exist can be gigantic and you can get wiped out by them. Whereas they're close to equilibrium, all you can do is not make a profit. There's a big difference between the two. So you've got mispricing, but it's too difficult to exploit or too dangerous to exploit. And I'll give you an example from another area of science, which is Lorenz's weather model. Now, have you heard of the expression the butterfly effect? Okay, well, this is where it comes from. A guy called Lorenz, and you'll see very clearly why they call it a butterfly shortly. What he was building was a model of fluid flow, where that's caused by heat. If you think about the storms we go home through, or the waves, the dynamics in ocean currents and stuff like that, they're all caused by heat differentials in a fluid. If you didn't have the heat differentials, you wouldn't have moving fluids. And the models that dominated meteorology when Lorenz was working were linear models, just like an equilibrium models, just like the ones economists use today. We're talking back in the late 1960s. And Lorenz was dissatisfied with these models and said he wanted to build a simple nonlinear model to show the impact of nonlinearity, but even he was surprised by what he found. So he had a model of convection in a fluid. And if you think about it, you put a pot on the kettle, on the stove, and you watch what happens, you'll see there's actually rising and falling columns of water. Well, that's what causes turbulence and storms in the real world. And it also causes that in the planet in which we stand, getting many, many earthquakes. You might notice that. It isn't, I don't think it is just a statistical aberration. There seem to be so many earthquakes and volcanic eruptions right now. There's some interesting research into why we're getting so many, and believe it or not, it's related to global warming. Now that's really a curly. We'll talk about that if you like in later discussion. But this is the basic picture of convection in the planet, because if you just if you imagine just unwrapping the planet, making a flat line, that's a picture of the Earth. We have 2,500 kilometres of molten magma below us. We're separated by that by a crust that's no more than 100 kilometres thick in most places. And what you've got on the heart of the planet is a core, a nickel iron core with large amounts of radiation inside there. And the heat coming out of that from both pressure and radiation is what keeps this planet alive. Now what you get because of that heat, this magma that's close to the core gets heated and rises to the top. And where it comes up, that's where you're going to get volcanoes, earthquakes, etc., etc. So that'll move the crust apart. We're talking enormous forces here. And of course, once it gets to the top, it'll cool down and it falls back down again. So that's the basic pattern you've got happening in any convecting fluid. This is just a good example from geology. And of course, when it gets down to the bottom again, it's cold, but of course it gets back to the region, it gets heated, and off it goes again. Now, Lorenz's model was looking at all these issues about how close together is this column of rising and column of falling fluid, and what the shape is of the convection currents overall. And he built a very simple model that only had 3 variables and 3 parameters. So you can't get much simpler than that. And one of them was the intensity of convection, which is just how rapidly is that thing turning over, how fast is it turning over. The second is the gap in temperature between the rising and falling currents. And the third was how much the profile of the temperature difference between the 2 columns differed from a linear profile. There's a linear profile, and there's 1 degree at the top and 10 degrees difference at the bottom. Then in the middle it's going to be 5. Okay? But if it's non-linear, then it might be 1 at the top, 2 in the middle, and 10 at the bottom. That sort of thing. So it's a measure of that curvature. And just putting that together. Now don't worry about the equation. I had somebody freaking out because they had equations setting up on the board, and I talked about them during the day lecture. I'm not going to pick anybody to reproduce this, but I want to show you how to model this and how, in what is actually an incredibly simple model, generates amazingly complicated dynamics. Now, the 3 variables there, on the dx dt, dy dt, and dz dt are the rates of change of those things. How much are they changing with respect to time? And over here, there's the rate of change of the convection between time, over time, the rate of change of the temperature gap, and the rate of change of the linearity of the profile between the three. Okay. And they're done in a very, very simple way. X, Y, and Z are variables that have numerical, just a simple scale of values. A, B, and C are numbers like 1, 15, and 6, that sort of thing. Very, very simple. You'd expect that a model that simple would give you very simple behaviour. There's 3 equations and 3 parameters. And if you look at each of the terms, they're a bit like what you might call the semi-quadratic. Like quadratic is y equals x squared. Well, this has the rate of change of y, for example. It's got z times x in it, just over here. B minus z multiplied by x. So you've got z times x there, which is like a quadratic in 2 terms, effectively. So, yeah, so we behave like an economist. Let's work out the equilibrium. Well, to do that, what you have to do is set all those rates of change equal to 0. Okay? If you're going to get an equilibrium, then neither the temperature gradient nor the convection can be changing, nor the other variable, the linearity of the profile. So you say, well, let's set them all to 0. Okay? And then what you get is equations you can solve which are linear and quadratic equations. The first one's pretty straightforward. If you look at to solve for the first equation, you get out of it that y equals x is an equilibrium. Okay? If y is equal to x, that equation is 0. So you've satisfied that first equation. So you know one particular solution involves the y value is equal to the x value. The second, you put x equal to y in the third equation and see what you get. And you get b minus z multiplied by y minus y is equal to 0. We'll take the y over the other side and solve it. What that gives you is b minus z is equal to 1. Okay? So that's another part of the solution. So z is equal to b minus 1 is the solution. And then you put that into the third equation. Substitute x is equal to y, so you get y squared, and z is equal to b minus 1. And you've now got an expression for y, but it's a quadratic, saying y squared is equal to c times b minus 1. These are just 2 of the parameters in the system. So there's 2 solutions for that, the positive and the negative square root. And finally, of course, the same solution applies to x because they're equal to each other. And also we know that if x is equal to y equal to z, they're all 0. That's also an equilibrium. So, oh dear, we have 3 solutions, 3 equilibria. Now an economist might think, oh well, the triple zero is obviously equilibrium. The other 2 must be unstable. No, bad news. They're all unstable. Every last one of them. 3 equilibria, and they are all unstable. Now, an economist's belief might be that therefore the system will break down because, and this is actually one of the leading developers of neoclassical economics, a guy called John Hicks, without knowing he was doing it, sabotaged the beginning of dynamic economics back in the 1940s by saying an unstable system doesn't oscillate, it just breaks down. And that was true of a linear system. It's false about one like I'm going to show you now, because once you've worked out the values and found they're all unstable, you can actually simulate them to see what they'll do. And I should have loaded another program here. You're going to be getting a program to work with later in the course that's being developed with a grant from the Institute for New Economic Thinking called Minsky. And I'll just bring it up here. Hopefully it can open at the right point. Let's see. Yeah, beauty. Okay. So that simple little thing, that those flowchart elements there, which are pretty hard to see, we haven't actually got the capacity to zoom in yet, unfortunately. So I can. No, there's no zooming possibility. But that equation there, for example, says x is the rate of change of x is y minus x multiplied by a, which is the first equation looking back here. So you read them in reverse, and don't worry about it now, I'll show you how to do it later. But I'll just simulate that model. And what you'll see happening, I've got the x value there, the z value down here, and for the fun of it I'm plotting y against x there and x against z down here. And if you watch it for long enough, you'll realise that it's doing some very, very strange stuff. Well, it's a bit strange already, I'm sure. But that system is currently orbiting around one of the three equilibria. There's the equilibria there. Now, rather than converging to it, it's cycling around the outside of it. And you might think it'll keep on doing that forever. You can see it's still changing over here. This is the x value. This is the z value down here. So oscillations are getting bigger.
Getting bigger and bigger.
Watch. Watch. Now you might think it's going to break down because it's getting larger and larger and larger. Okay. Now it's orbiting around that one. No. It's entirely deterministic. There's not a single element of shock or disturbance inside. It's an entirely deterministic system. But it will oscillate forever. So a nonlinear dynamical system never can actually go on indefinitely without ever reaching equilibrium. Because now, remember I mentioned there are three equilibria? That's one. That's the positive values of x and y. That's the other, negative values of x and y. And the third one, 0, 0, 0, is in the middle there, and they're all unstable. The system oscillates away from each of the equilibria. They're what are known as complex, as strange attractors. They attract and repel at the same time. Pardon? Pardon? No. No, it never goes to 0, 0. It goes past it, but never stops there. If it stopped there, it would stop in the middle. And see what happens? It gets there and it bounces away again.
But it always makes back to that same point, does it?
It's not actually the same point. If I actually did it in 3 dimensions, you'd see it was missing 0, 0, 0. It's a bit like a meteor that goes straight past the Earth, zooms around the sun, comes back again, misses the Earth again, and just keeps on doing it indefinitely. Okay, so it's heading towards the Earth, but it never lands there. And that's exactly what's going on here. I'll show you this. This is a developmental program. We're still a long way from finishing writing the software, but it gives you an idea of what can be done. And you're going to get that one for free. Let's bring up my animation from. I'll show you what that looks like in a sexier program, but one that's is better suited for the sort of dynamic stuff I've shown you a moment ago, but not as good for what we're going to do with banking later. Here's the same model. And down the bottom I've got the x and y shown independently. This is what Lorenz first showed when he got the model plotted out. These are the dynamics, so he didn't see the x-y plot. And he was stunned by it, thought there must have been a mistake. So he got the person who was programming it for him on a really primitive computer that had 6 digits of accuracy internally and printed out in 4 digits. And he said, feed in the same values again and see what happens. And the guy fed in the input, but it was only 4 digits of accuracy. So it started with 6. And what happened was a totally different time pattern, which really surprised Lorenz. So all the stuff about chaos theory and sensitive dependent exponential conditions came out of that. That's the sort of pattern you see happening. What it's building in the background is that effect. And it's a bit easier now to see in this one with the graphics. You can see that there's 0, 0, 0. You don't quite hit it. You go past it. So that's the first example that we got in a practical sense of a nonlinear system. And it never reaches equilibrium. In fact, the equilibriums, as you can see, are repellers. There's a vacant space around both of them. You won't get there. If you start there, you get blasted away from them. So that's a genuine dynamic system. And what I'm doing to model it there is using numerical techniques that engineers and scientists have developed to handle this stuff so they actually see what's going on. And the basic idea behind it is quite simple. You take some variable like population, multiply it by its current rate of growth, integrate that, and add that to the original population, and you've got an estimate for the actual population now. To give you an idea of that, here's a model that does that using program DivSim. So you start with population, you multiply it by its growth rate, you integrate that, and the 1 over S there is a quirk in the history of how these things were developed. They use what are called Laplace transforms, and that's just part of what's called a Laplace transform. You add it to the population when you started from, and that gives you your estimate of population now. So I'll just show you how to build a model like that in this program. I just, let's get a new one here. And I need a variable which I'm going to integrate. So bring this down here, double click and call this population. And say it starts at, say, 20 million. Right click and copy the variable, bring it over here. We know constant, say, called GR for growth rate. Be anything you like, but that'll do. And say growth rate, say 2% or 3% per annum. Your fast rate of growth. Multiply together, and what you do to multiply is just wire them up. Integrate it, that's population. Bring a graph down. Pardon me, attach. And simulate. That's a differential equation. Now I'll be getting into much fancier stuff than that when we get to the stage of modelling monetary dynamics later, using a feature this program has that others don't, which is the capacity to model a banking system by using double entry bookkeeping. So that's coming your way in about 4 weeks' time. But that's the basic idea of doing a dynamic model and simulating it numerically.
So is that just doing population times 3%?
Yeah.
Then that was all times 3%.
Hadn't they know?
So for year 1, it's 20 million times 0.3.
Yeah, 0.03.
And then,
which is 600,000, which becomes 20.6 million, which is then by 0.03 that. That's right. And actually, to keep on going, as I've shown here in this plot, with a 1.5 population growth rate, if we started with 22 million Australians in 2010, by 2110 there'd be 98 million Australians.
But how does it know the relationship, the correlation between growth, economic growth, and population growth?
That's where you've got to make the model more complex. This is incredibly simple in just saying we can grow like that forever, which we can't. Okay. So you put in feedback systems. That's what's going on in Lorenz's model. All that stuff is feedback between the X and the Y and the Z values. So without the feedback, they could go anywhere. With the feedbacks, they constrain each other, and you get much more complicated dynamics. And that's the sort of thing I'll be showing you how to model as we get later in the course. I've also embedded a free copy of the program in this presentation, by the way. So you can download it and take a look like it. Now that's Lorenz's model. I think actually, I've tried to design the software I showed you a while ago, so it's actually easier to use and easier to look at than these systems. I don't think my Lorenz is easier than that one, but that's another story. I'll get you to... Pardon? Yeah, it is. You mean like a circuit board? Yeah, it's very much the same type of technology. And in fact, there's software packages that simulate it. You work in engineering, or but you've seen programs where things like the chips you all use in your computers are first of all modeled in software before they're made, and they're modeled with incredible accuracy. So if you actually, a colleague of mine who now is president of the International Electrical and Electricians and Electrical Engineers Association in America, global organisation. He wrote one of the software packages that was used by Motorola to design chips, working out what level of semiconductor doping you needed to get the type of characteristics you wanted and so on. So it's all simulated in software before they build it. Jim told me once that he was got an idea. He's a very, very, very humble guy, very down to earth, and he'd done the design for a new Motorola chip, and he realised there was a flaw in his program. He had a bug in the software, and he said he rang down quickly to tell the production line to stop making that chip. And he said we got a call back later from about 10 minutes later from the manager saying, "Oh, we've got your instruction, Dr. Prendergast, and we're waiting your instruction before we start the line again." He went, "Cool, I could do that." He got an idea of the influence he had. Well, his software was specifying exactly what the hardware is going to be. So this technology is commonplace in engineering. If you're doing an engineering course, you'll be learning this stuff in the first few weeks. So to me, it shows how primitive economics is. There's nothing like that. You're still playing with toy intersecting line diagrams and third and fourth here. I'm trying to get away from that. So what you can see when you have a model like that, even if it's a simple system with 3 variables and 3 parameters, you get complex cycles, which are unpredictable, but there's a structure at the same time. And that structure is kind of beautifully seen in what we call Lorenz's butterfly. So it looks like total chaos over here, has this sort of structure down here. Quite amazing. So, and what it can explain are the dynamics of weather. So if you look at a pattern like a cyclone here, then what you're actually seeing going on in 3 dimensions is this vortex of spinning air. Okay? Up it goes, descending air in the middle, rising air on the outside, and that cycle is the basic structure of the weather system. And there are now, working from those 3 simple equations Lorenz had back in the late 1960s, there's now an enormous development of meteorology. It's why you see those fantastic graphics on the weather when you watch the news. That's not an animation. That's a simulation being shown on the television of a mathematical model of the weather. And the model, the last time I checked, the model that they use, the dominant one, runs on a bunch of supercomputers in Tokyo and models the Earth's atmosphere down to 100 meter cubes, and actually includes chemical interactions that are occurring above cities, as well as temperature changes and what's happening in the ocean and so on. So incredibly sophisticated, become a huge way. Economics is still in the dark ages. Now, could we explain using this sort of idea, this sort of approach to modelling, what happens in stock markets? And somebody called Benoit Mandelbrot didn't think that was the case, and he actually was the guy who brought chaos theory into economics. He did it at the same time that CAPM came along, and the profession completely ignored his ideas about chaos in financial markets, and he gave up on trying to convince economists about it. He actually moved across to geology and worked in geology for quite a while, and geometry too. And he thought if stock markets were efficient, as economists say, then prices should follow a random walk. And that's not, he looked at the data and you could superficially think it's random, but a careful look at it shows that it wasn't random. And his work on that was ignored. But if it was true, then what you get, generally speaking, would be something that looks like a variable, a variable subject to random shocks. Okay? Coming in from the outside, where the shocks would generally be Gaussian in structure. There's a range of different distributions they can follow, but they all converge if you take enough samples of them to the Gaussian distribution. And there are things like tossing a coin, which is binomial. If you throw the binomials often enough, you can estimate it using a Gaussian, rolling a dice, spinning a roulette wheel, etc., etc. In the limit, if you do them often enough, then you can describe them just using the average and the standard deviation. That's all you need. If you think about what you're taught in finance, you're told, let's work out the stock market using the average and the standard deviation. That's it. That's all the information you're supposed to have to use to work it out. Well, if that's true, if that were true, then once you work out the mean and the standard deviation, 68% of all events should fall within 1 standard deviation of the mean, 95% within 2, 99.7% within 3, and ultimately nothing should happen more than about 5 standard deviations away. The number of events that turn up that high, those are simply trivial. Now, I'll give you an example. We're looking at something which is Gaussian in distribution, and that's the height of American males, who average 178 centimetres with a standard deviation of 8 centimetres. there's roughly 150 million of them, so the height distribution should look like something like this. Looking at the height of American males, and then the thousands that actually got that height. That's the sort of shape you should get, most converging around the 168 mark. And if you then rank them from the shortest to the tallest American, that's what a Gaussian prediction is. And you notice down the bottom how it starts from 0 and goes rapidly up, meaning there's almost nobody who's less than 160 centimeters tall. Okay. And then you get up to where you're getting up to 140 million worth of them now. There's almost nobody more than 2 meters tall. There are some, but very, very few. So the vast majority lie between 170 and 190 centimeters tall. Only a tiny fraction are taller than 2 meters, which is 2.75 standard deviations above the mean. Or shorter than 160, which is 2.25 below. So again, plotting what percentage of the population is taller than a particular height, you find that virtually 100% are taller than 160 centimeters. And almost nobody is taller than 2 meters. Of course, there are some. That's looking in the other direction. Looking the same way with standard deviations. So once you get to even 3 standard deviations, you're down to a tiny fraction of the population that actually is outside that range. Now the stock market did the same thing. Then similar characteristics would apply there. So using the average and standard deviation would tell you all you need to know. And 68% of all movements should be within 1%, 95 within 2, and so on. So here's the Dow Jones from 1914 to 2009, and the average daily movement across the whole range is 0.27%, very quite a small movement. The standard deviation is very big, rather different to the height thing I showed you, we'll find it the other way around. 1.136 is the standard deviation, roughly 25,000 trading days. So what the market should look like is this, because you feed those parameters into a random number generator, and that's what I'll give you. So that's what the stock market, if it were truly random, that's what it would look like. You reckon it looks like that? That's what it looks like. Okay? Some pretty big exceptions. Massively outside. That's 15 standard deviations up and 22 standard deviations down. Give you an idea of that. What is 22? 23. If that happened in height, you would occasionally see an American who was 4 meters tall. Now, some of them might think they're that tall, but it doesn't happen. But it does happen on the stock market. Now, if I sort the random numbers from the smallest movement to the biggest movement, that's what it looks like in terms of a simulated data that I've just shown you a moment ago. The vast majority of movements were more than minus 3 standard deviations and less than plus 3 standard deviations. You can pretty much ignore anything outside that range. The actual data, at first glance, doesn't look all that different. Here's the comparison of the actual data to the simulated. So the simulated is the red line and the actual is the blue. Now, across that range doesn't look all that different. But clearly the blue goes out further than the red does. So I've just truncated it there, which is the sort of thing an econometrician might do. Cut out the outliers. Ignore the outliers, they're so small. Well, let's do it without removing any of the outliers and see what it looks like then. And oh boy, is it different to a standard deviation, the standard normal distribution, because here I've shown from minus 24 up to plus 16% changes, how many trading days lay within that range. So there's one trading day somewhere in the Dow Jones history where the market gained 15% in one day. There are 10 days where it gained about 9%. There's 100 days where it gained 4%. Now, according to this, there should only have been about 3 days in that time period where it gained 1% or 4%. So there's an enormous difference between what the model standard deviation plus normal distribution gives you versus what the data is actually like. So there's daily movements as large as minus 22%, and there's many, many more positive events that are as large as 15% there. Bring that down a bit. Okay. So simulated data looks nothing like the actual data. Just a simple visual, you can tell that they're totally different. So they've got the same number of points, and you get a much lower prediction of how the range of movements coming out of the simulated data than you come out of the real data. So here again, looking at the negative movements, negative to positive, and saying how many trading days had a movement of more than that amount. Well, there was one trading day with a minus 22%, whereas according to the random distribution, there should only be one trading day with a movement of 4%, 1/5 as much. So the random walk is much, much shorter than the actual data. That's the random's total range. That's the range of the actual data. And because it's such a much bigger range and there's so many events, the events in the tail actually determine more of the shape of the outcome than in fact the ones in the middle do. So you get a prediction of one movement of minus 4.46 is the worst ever. That's the way you read it. Look up from the bottom as a percentage change, horizontal is how many days were of that scale. In fact, there are 100 days. You go up to the blue line now to see what the story is there. So events, a 4% movement in the market was 100 times as likely in the last century as would be predicted by saying it's subject to a random walk. So it's got a drastic underestimation too at the level of volatility. So this is looking at across the whole time period and saying, okay, rank them from the biggest movement down to the next biggest and so on. And you start at minus 22%. And even by the time I've got to the 33rd largest movement, I've still got minus 6.9% there. Now looking at the random data, the worst I get there is minus 4.46. And by the time I get down to the 33rd, I'm saying it's minus 3.5. There's an enormous difference in the data, and there's also clustering. There's an extreme, those are the extreme falls. They don't even turn up over here. The 33rd largest actual fall is 3 standard deviations bigger than the worst prediction of a random distribution. And there's also clustering going on. That's all the ones from the 1930s. Over here, it's a random distribution through time. So just reading off you've got 1941, 73, 56, 17, 24, 87. Sounds like a bingo game, doesn't it? Okay. You try the actual data, and it's massive clustering. So the actual data goes 1987, 29, 29, 31, 29, 32, 32, 87, 2008. 1930, 33, 2008, 2008, 1917. That's the first exception from being either the 80s, the decade we're in, or the 1930s. So there's much more clustered information as well. All paradoxes from the point of view of the efficient markets hypothesis. So all this stuff that it argues is the opposite of what the theories I'm going to be taking you through argue. And in fact, they are much more like the data. Distributions are called fractal. I'll explain those more in the next lecture. And when you have a distribution which is fractal rather than Gaussian, you get many, many more events in the tail, but you also get many more events around the mean. The middle tends to disappear. And you can get enormously large movements. So again, just to emphasize the difference, the random walk approach says that there should have been less than 2 in a million chance of a 5% fall in the Dow Jones in the last century. 2 in a million. That's how many times it can happen in a century. You'd need 1 million centuries before you'd see 2 movements of 5%. In fact, well, actually 2,500 years, pardon me, when you actually extrapolate the linear there, my mistake. But what you get is what's called a power law distribution. And that's when the number of the events of a particular size is roughly proportional to that size raised to some power. And in the case of the Dow Jones, the number of events of X% movements over a period of time is roughly equal to x raised to the power of minus 3.96. Now what you get out of this is a straight line relationship. You work through the logic there. The number of events of scale x is going to be equal to x to the minus a. And then the log of the number of events is going to be equal to minus a times the log of the scale. And that applies to a whole range of different phenomena. Earthquakes, size of epidemics and all sorts of things. And what about the stock market? Well, that's the value I got. Number of events of x percent is equal to x percent raised to minus 3.96. And I plot it. The dotted line are the binned changes over particular ranges. The straight line is my prediction. So down the bottom, what you've got is the log of the percentage change, and minus 1 means 10 to the minus 1%, which is 10%. So I'm saying, what's the odds of a 10% change? Well, according to a power order prediction, the odds are 1 event every century, actually about 6 events every century. The actual data was 8. That's pretty close at the extreme scale. Now, compare that to the Gaussian prediction. The green line is the Gaussian prediction. Now, what you notice about it, it's massively wrong for the big movements, but it's pretty damn close for the small ones. So if you actually trim the data and leave out the outliers and fit, you'll get a really good fit out of the Gaussian prediction. Yeah, natural phenomena. Well, see, some natural phenomena activate power laws, earthquakes do, for example. So it's not so much natural, it's saying it's totally random. There's no causal relationship between one event and another event.
What's the power law used in natural phenomena?
That's, yeah, pardon me, yeah, natural phenomena saying things were related to each other.
Well, plugging it into the market.
Yeah.
You need to use the natural.
In saying that there are feedbacks, so one event does have some effect on the next event. If you roll the dice, so if I had 100 dice in my hand and threw them on the floor, the odds are they'd come out to 3.5 on average. Okay, but if you have a stock market, then one person's behaviour will cause somebody else to behave in a different way, and then the feedbacks that occur will give you effects of like an earthquake, where one earthquake can trigger another earthquake, and so on. And so a better model for what's happening here is actually things like earthquakes. The first effective model is called the sand pile model of this. Imagine you've got a bucket of sand, and you're pouring it on a flat surface, and you constantly pour the sand as best you can onto the top of the point, and you watch what happens. What will happen is it build up, get to a certain point and go flop. Okay? And then it build up again and go flop again. And so the slow accretion of sand leads to a stable process for a while until the edges get too extreme, and suddenly they'll all collapse. And then you get another stable system, so it happens again. So that was the best model we had initially for stock market behaviour. Period of what looked like stable returns, then a big crash, because the forces involved are building up all the time.
Are there any models that you can draw on from unrelated things that give you an estimation of when, or if you go back and test when these prices occur?
There's a guy called Didier Sornet who's trying to do that. He's using models that are based on very strange mathematical functions called Weierstrass functions. Didier's actually stuck his neck out by making his predictions in a file he can't edit and saving it on the web with a signature so you can open it and check it later and see whether it's been right or not. He hasn't been all that accurate in terms of predicting when a crash is going to occur. What he has been good at is saying after the crash occurs, this is the time pattern the system is likely to follow. He calls it a log periodic function. It goes down, bounces up again, down, and bounces up again. And the oscillations start up very large and then get smaller before you run away from the impact of the crash. So that's been fairly accurate. And lots of people are using systems like this to try to work out which way the market's likely to move. So there are people with algorithms based on this, and chaos theory, and a whole range of other areas trying to pick the market. And of course, because they're doing it, they're changing the market. So the flash crashes we're seeing right now are partly a phenomenon of that. It's a complex world out there, nowhere near as simplistic as the neoclassical model is. And then their practitioners now
Far more interesting.
Far more interesting. boring as batshit the way the neoclassical economists treat it. You know, if that was the case, there'd be nothing to talk about. You know, you'll all be agreeing about what's going to happen to IBM shares. You'll be right about the future. Uncertainty, what the hell was that? But yeah, it's much more interesting stuff. And I'll be giving you some references to take a look at. I don't actually go a great deal of detail on this, but I really want to talk about the impact it has on economics. Because once you, as I say towards the end of the lecture, once you acknowledge this stuff, you can't separate finance and economics anymore. You've got to have a combined theory of both. And I'll be covering you through that. But again, looking at this stuff, great in the minor range, plus and minus 3 standard deviations, hopeless for the large stuff. So again, prediction of how many 6% movements, 1 per century versus 57. Predictions of 8% movements, or minus 8, 1 in a million chance per century versus 11 in the last century. So to read this particular chart, on the bottom, minus 1.2 means 10 to the power of minus 1.2, which is about 6%. And over here it says they're going to be 10 to the minus 2 such events, which is 1 such event every 100 centuries. The actual number, read up the same line, 57. Over here, Gaussian prediction is of a movement of 8%, is 10 to the minus 6 such events per century, which is 1 event like that every million centuries. And the number, 11, last century. So massively, massively wrong at getting what happens in the extreme events. So you've got this belief in an equilibrium system where change is due to random shocks and therefore big changes are vanishingly rare, but the actual data gives you massive big changes are extremely frequent. This is, again, I'm going to put a few slides, I might jump through a couple of them. You can check themselves out later, I'll just explain how to interpret them. This is saying, given me a range, plus or minus 1%, how many events were there? And what's the Gaussian prediction using the mean and standard deviation? Pretty damn accurate. The difference between the two, the ratio of one to the other, is 0.96. How many of 2%? Again, pretty damn close. Very close ratio. 3%, closer still. So if you stick at plus or minus 3%, looks great. You can believe you've got a good model. Go up to 4%, 4 times as many events as the theory predicts. 5%, 38 times. 6%, 1,000 times. 7%, 53,000 times more such events. You get down here, infinite difference. Okay. So it's a totally misleading model about how the world actually works. So you can have any size crash, and the likelihood of happening is far higher than you'll predict using the Gaussian model. So rather than crashes being aberrant behaviour, it's actually the standard behaviour of the stock market. And there are crashes on all time scales. So here's a few comparisons. That's looking at a graph of the actual versus the predicted, given plus and minus ranges around the mean. You can see close to the mean, pretty reasonable predictions. At the either extreme, hopeless predictions. A similar thing here with the actual versus the predicted, showing what the actual data says and how many are predicted for less than minus 6 or lower. Over here, plus 6 or higher. Another way of making the same comparison, the ratio of the actual events to the prediction of the Gaussian model. So many, many ways to say this just doesn't cut the mustard. Now, I can give you and I'll go through in a couple of lectures, or the next couple of lectures, more sophisticated ways of looking at the market that actually do characterise the behaviour, but it comes out being partly deterministic. If you're saying it's not Gaussian, not totally random, there's got to be some structure to what's going on. But it's highly non-linear, battle between bulls and bears, cash running in and out of the economy given what's happened in the overall broad economy and so on. So we need a theory that brings that all together, a non-linear, a non-equilibrium theory of finance, and the theory of endogenous money as well, that also ties in. And the intriguing question is, why do so many economists still cling to this stuff? I'm sure you're still being taught it in finance courses here, correct? Okay. It just is so wrong. Let's talk a bit about